Hello everyone, my name is Ghorbani. I'm the Associate Professor of People's Financial University of Russia. The topic of our research is studying the possibility of algorithmic compensation of temperature instrumental errors of string accelerometers as a compensation of the strapdown inertial unit. The navigation system is basis and core of realizing the autonomous control of completing the task for unmanned vehicles, and the strapdown inertial navigation system is the preferred due to its autonomy and independence. It is used for aerial photogrammetry, marine monitoring, geodetic surveying, hazard state investigation, and security protection based on different sensor equipment. The navigation information of the unmanned vehicle provided by its navigation system includes the position, velocity, the heading, and the horizontal attitude. This is the premise and the guarantee of the normal working. The accelerometers are used to measure the specific force and gyroscopes for the implementation of an inertial frame of reference. The accelerometers provide the sensor output, which plays an important role for position. The accuracy of the strapdown inertial navigation system is mainly affected by the errors of the sensors. One of the main factors is temperature, of course, which affects the stability, accuracy, and reliability of an inertial navigation system. The temperature variation of environment and heating in operating systems cause the temperature accelerometer and electric circles, which may vary from zero offset and scale factor of accelerometer. So the purpose of our study is to propose an algorithmic compensation to measure the temperature error of the initial frequency of a string accelerometer used as a part of the strapdown inertial system. The study consisted of collecting output information from the device during its temperature calibration of string accelerometers. During the experiment, the strapdown inertial system was oriented in space so that its measuring axis of the accelerometer channels were directed alternately vertically upward or vertically downward with a smooth temperature change. In addition to the string element itself, the accelerometer includes an information pickup device, and the string excitation device was developed by a company in POIT, Russia. During the experiment, we studied the change in the initial oscillation frequency of the string accelerometer and the design parameter. During the calibration, the instrument was periodically turned off for 1 minute, and then one measurement was performed. The instrument was turned on for 10 minutes, during which the values of the parameter f, the vibration, the frequency, and the design parameter was measured. Based on the results of the studies of the condition of measuring the instrumental errors of the information management system channels in the operating temperature range, the measurement of the instrumental errors of the linear acceleration sensor channel was carried out in only one measurement condition: continuous temperature change from the -16 to 50 degrees when the linear acceleration sensor channel was turned on or off. The output signal recorded by channel information management system was carried out within 200 seconds after each 60 seconds. After power supply, time of test, object readiness was 60 seconds. As a result, we get the change in the initial oscillation frequency of the string accelerometer in the operating temperature range, and of course for design parameter for 3 different cycles. As can be seen from the graphs, these parameters have good repeatability, which allows us to conclude about the deterministic nature of changes in these parameters with respect to temperature. And the change, okay. The verification of the obtained approximating functional or dependence of the coefficient of the polynomial of approximating function of frequency and design parameter in different temperature interval was carried out by using these equations. Then we got the based on the result of the verification algorithmic compensation error for changing the frequency and design parameter was obtained. And it follows from these two figures that the efficiency of applying an algorithmic compensation for the change in the coefficient of frequency and design parameter, which are proportional to the elasticity of the accelerometer string and the obtained polynomial approximating functions, are quite high. It is difficult to distinguish a component of the error that slowly changes with temperature, so that the nature of the changes in the error is close to the random process. As a conclusion, I would like to say that we, in this paper, the temperature of the initial frequency of accelerometer and design parameter was studied and measured. It shows that the use of this algorithmic compensation for temperature error they reduced the frequency from by more than 2 times, and the for the design parameter, it is an almost order of magnitude less than the value before algorithmic compensation. Thank you for your listening.